So thanks for giving me this opportunity to talk to you all. As was introduced, a synthetic organic chemist and have a deep interest in origins of life chemistry. So let me begin by, you know, so this is the molecule RNA as drawn in many textbooks that you might have seen. It consists of a sugar called ribose, a phosphate linker, and the four nucleobases that we know of as the alphabets of life. And people have been wondering about this. So there are the two different kinds of bases. You may see a purine and a pyrimidine. And it's very nice to, let me just start my timer so that I do not run over. So the question, people begin to wonder is, why these kind of molecules? So if you walk to somebody in the street and ask them, when I say sugar, what is the first molecule that comes to your mind? It's glucose, fructose, sucrose. Very rarely people say ribose, because ribose is always part of the nucleic acid RNA. And it is connected in a very specific manner with what we call a nucleosidic bond, connecting the bases to the sugar and the phosphodiesters to the sugar as well. So this is my professor under whom I trained, Albert Eschenmoser, who started asking these kind of questions. Why a 5-carbon sugar? So if you count the number of carbons, 1, 2, 3, 4, 5, it's a 5-carbon sugar known as a pentose. But then among the pentoses, there are 4 different pentoses. Why ribose? And then why this 5-membered ring? This furanose refers to the 5-membered ring. Why this 5-membered ring and not a 6-membered ring? Then there was Westheimer at Harvard who asked the question, why a phosphodiester? Can't this be another linker? Why these kind of molecules? Then there was the famous, Crick, who was at the Salk Institute along with Leslie Orgo, who also asked the questions, why these bases? Why can't it be something else? And in essence, why the Watson-Crick base pairing with the structure? And the whole question now is more philosophical for us, like why RNA? Not how these molecules were formed, but why these kind of molecules were selected by nature. So, and this was expressed beautifully by Albert Einstein, who said, we not only want to know how nature is, but also want to reach, if possible, a goal which may seem utopian and presumptuous, namely, to know why nature is such and not otherwise. So why these kind of molecules? And you can ask these questions for why alpha amino acids, why peptides, why phospholipids, and you can generally ask the question why. So it's a question that goes not just beyond the chemistry of these molecules, but even touches upon their function. And that's what I would like to present here. So one of the things that Eschenmoser did was, when you are a synthetic organic chemist and you ask this question, you can begin to answer these by making the unnatural ones. And one of the things that is very profound in these kind of scientific adventures is that when you want to understand why a molecule functions as what it does, it's important to make an alternative to understand what is gained or what is lost when you change the structure. Only then you can begin to understand the question of why a molecule is important, rather than just studying it by itself. So one of the things that he started doing was, okay, if you assume different kind of molecules were available on early Earth, why did nature choose this kind of a structure and this kind of a structure? And so what he began to do was, as a synthetic organic chemist, he started putting in different sugars. So he took the ribose out, started putting the different sugars in there and seeing what the base pairing properties are. And it turns out that they have very little or no base pairing, the Watson-Crick base pairing that brings backbones together to form a double helix. But when he switched the same sugar, the same 5-carbon sugar, went from a 5-membered ring to a 6-membered ring, all of them were much stronger base pairing than what is found in nature. So you just can't conclude that there is no base pairing, therefore it does not function. But some systems are there which even are much better in terms of their strength of base pairing than what nature is using. So he concluded there must be some sort of a just right selection criteria that must have selected, and then he concluded that there must be an optimization of a system rather than the maximization of a. If you want to connect, something like the happiness that was talked in the previous one. So there is an optimal place where it is just right for these molecules to evolve. And so when we people like chemists, synthetic organisms try to understand how such a molecule could have appeared on early Earth. We think of these kind of simple molecules, energy sources that might have existed 4 billion years ago. And then we start thinking about RNA-specific building blocks that would make RNA. But then there was also a group of people who said maybe RNA is too complicated. We could look at things that were much simpler than RNA, which give rise to an RNA. So they called it a pre-RNA. And one of the things that people said was, if you want to work with a pre-RNA like molecule, you need to think of certain criteria that must fit the same type of criteria that you are using for the emergence of RNA. So this is generally the model that people use. A mixture of molecules and earlier. From there, molecule arose that kind of an XNA or what we call a pre-RNA or directly to an RNA. Many people prefer direct takeover. And then RNA invented proteins, then invented DNA, and now we have this RNA DNA. So people have so many different variations. So here is the canonical nature uses, and people have varied the sugar backbones quite a lot. And even acyclic systems like the very famous peptide nucleic acids, they all have base pairing properties to a certain extent. But when you start changing the bases, you kept the four bases AUGC common, and you change the backbone. But what we began to do in our lab was to change the bases as well. And what we found surprisingly was that there were very few bases that would function like in a base pairing structure that you see in the RNA. While with the four bases, you can vary the backbones quite a lot. You are not that versatile in varying the number of bases. There are very few bases that would function the same as AUGC. And we started wondering why. Why is that? And one of the things that we found out was there is this chemistry students and biology students know is an ability of a molecule to donate hydrogen in order to make a hydrogen bond. And what we found was when we started looking at a pK number from this is highly basic, this is highly acidic, this is highly 7 is neutral. What we began to find was that the natural bases that were base pairing in our previous unnatural ones, they all clustered around 10 and 4, whereas the ones that were not base pairing around 7. And this led us to a realization that if you are in water is usually the solvent of life. That is where life occurs. So if you start taking and putting these molecules in water, what happens is now begins to interact with these molecules. If you are having a pKa that is the ability to donate a proton or take a proton within the same pH of 7, which is close to neutrality, of water, what happens is begins to overwhelm your interaction. Instead of these kind of molecules which have a pKa farther from 7, what happens is these are hydrophobic. They don't like oil droplets. But whereas these they are hydrophilic. They would like to interact. So what happens is when the two strands want to come together, water molecules interfere and they keep separating them all the time. And so what happens is the bases that nature has chosen are like oil droplets. When the buffer pH in your body, which is close to 6.5 to 7, is where the Watson-crick base pairing happens. So if you can imagine, when Frank Heimer he said why phosphate, and he said the pKa of the phosphate is far away such that it's always ionized, and you need these, your DNA, RNA backbone to be ionized, because otherwise they will not dissolve in water, and they need to be stable, and not hydrolyzed and that is what is important. When you look at these canonical nucleobases, whose pKa is around 4, which acts like the answer is exactly the opposite. Here they are hydrophilic, and here the answer is of being not ionized. That means they are the exact opposite of phosphates. What happens is they act like oil droplets, they will find each other in water, and then you have the AUG pairing with the UG pairing like a handshake, which is the two hydrogen bonds, and then you form this beautiful double helix, then forms the basis of your information that gives rise to the translation, the protein machinery, and etc. that leads to life. Water is very important for hydrogen. So when we started looking at various nucleobases, alternatives, what we found was depending on how you change the hydrogen bond donor or the hydrogen bond acceptor, what happens is you can have if you take water as the medium, this system they will show a huge difference, because we have just changed one atom here. But if I put it in an organic solvent, like say chloroform, they both will become strong. That means the solvent determines what sort of a system you can have for base pairings. The RNA and DNA that we think of essential to our life is only possible because of the solvent water. If we have, if the world was always like chloroform, we would not have had RNA and DNA. We would have had a very different system. So by asking this question why and making other components, we can really move forward, by getting these insights as to what is very important for these life molecules to function and operate and give rise to this emergent property that we call life. So if you imagine an ancient, ocean, which had a pH of roughly 7, close to neutrality, and then you begin to assign all the nucleobases that have been studied in the, lot of other senses as well, like the antisense in medicinal chemistry, the antiviral chemistry, and you take all those and start putting the pKa numbers, what you find is actually at a pH 7, there are 2 dry islands that just pop up. And one dry island and the other dry island are exactly around the pH 4 and pH 10 we talked about, and most of them are the natural nucleobases. So what it means is when nature decided or when nature chose these type of nucleobases, the pH must have been around 7. Because if the pH was less than, let's say 4 or close to 10, these bases would not be selected because they would be part of this, they would be submerged in water. They will have a handicap of base pairing. So what you begin to see is there is a direct correlation between the early Earth environment and the type of molecules that life had selected. They are coupled together. You cannot decouple them. That is why when you want to, biochemists will know when you want to denature a protein or denature nucleic acids, you simply change the pH or put them in organic solvent to denature. And that is why. So the function of a biomolecule depends very much on the environment. And here it is the solvent and the pH of the solvent. So there is a domino effect of this. This pKa minus pH, which is very fundamental, a physicochemical property at the level of a molecule, really translates to a much higher order level. And you can begin to ask these questions, why a purine pyrimidine? So the uracil is a pyrimidine, the adenine is a purine. So it's a purine pyrimidine and a purine pyrimidine. So why can't it be a purine or a pyrimidine type base pairing? This was a question that was raised by Leslie Orgel and Watson, the Crick of Watson Crick. So one of the things that we found was this is something that people know very well. This is like the soap that you use. So the soaps are made up of these kind of long chain fatty acids. Here they are called phospholipids. And when you put them in water, they begin to aggregate based on their what is known as a hydrophobic interior, which is the long chain fatty acids, and a hydrophilic exterior, where are the phospholipids, the phosphodieesters, which make these negative charges. And what we found was you can view your DNA and RNA exactly like that. The DNA and RNA also have an outside phosphodiester backbone, which is hydrophilic. You have the hydrophobic bases that are like the fatty acid chains. And therefore, this led us to a model where we can begin to predict if you take these kind of, the longer bars are purines, the shorter bars are the pyrimidines, like the A, U, G, C type. And what you begin to do is now you can play a game. So if you draw a line of this and then you make a purine, where then now the two longer bars are together, whereas the pyrimidines, where the shorter bars are together, you can begin to see that when you bring these, remember, these are negatively charged phosphates. So when you bring two negative charges close to each other, they begin to repel. And when you make them too far away and you increase this hydrophobic core, which makes it very strong, what happens is that these systems become very, very strong. These systems become very weak. And this again is that Goldilocks right for optimal of base pairing. And this we know from another research from Stanford, where Eric Kuhl, what he did was he took the purine and the pyrimidine bases and made them longer. So he really made a purine type base. And what he found was that when you introduce a mismatch, so remember the DNA and RNA, they talk to each other based on the AUGC pairing. If there is a mismatch, it leads to mutation and leads to diseases and things like that we know of. So what you see is that this extended DNA, what he called Y-DNA, has a high degree of tolerance to mismatch, whereas the DNA, even if you make a slight one single mismatch, the whole thing falls apart. And that is what you want for a system to faithfully reproduce and copy the information. You want a system that is optimized for reproduction with high fidelity. And these longer ones, which are very strong, they fail to do the job. So you again begin to see why a purine pyrimidine would be the best in terms of optimization of a base pairing. And this is again within the context of a ribose backbone and with respect to water and the pH 7. So everything is interrelated. You just can't pull one thing apart and say it's only because of this system has been chosen. And now you can even ask these questions further, where you can begin to say, okay, why Watson-Crick? There is the reverse Hookstein and the Hookstein, and there is a very famous story of how Watson and Crick came across this thing with, of course, Rosalind Franklin's X-ray structure. So that's the Watson-Crick. And the reverse Hookstein is also there. And, there is some biological functions based on these kind of different types of base pairing that is known. But nature, generally, when you look at DNA, the beautiful double helix you see, it's the Watson-Crick. So, and then, there are the B forms and the A forms of DNA. And you can begin to see how, so this is the usual picture you see. You Google DNA and RNA and these kind of structures will pop up. But so remember, this is a double helix. So if you take the double helix and turn it and look down the double helix, what you begin to see is a marvelous difference between the two. Here you can see how the bases are towards the edges. And in this BDNA, you can see how the bases are towards the center. And here you can see how they are, a little scattered around. And remember, these bases are hydrophobic. They don't like to interact with water. And if they don't like to interact with water, this BDNA is the best way to stack them in the center and keep them far away from the water molecules that surround the phosphodiester bonds around that. So you now begin to see how that hydrophobicity, which results from the pKa minus pH relationship that I talked about very early, has even led to the preference of BDNA over that. And you can also see, so people have tried to force the DNA into a Hookstein form, and you can see that here is the beautiful B form and X-ray structure of that. And the same molecule, when they substituted with the bromine on the uracil, they give a Hookstein, and you can begin to see how that has been disturbed. That beautiful symmetry and the placement of the bases one over the other has been disturbed and leads to a structure which suffers a little bit in terms of hydrophobic interactions and hydrophilic interactions. Therefore, what you can begin to see is this hydrophilic interaction, which again relates back to the pKa minus pH relationship, really determines how you go from that small interaction of hydrogen bonding to two structures coming together, and then begins to really you know inform you and tell you why that small difference in the pK minus pH has actually ballooned over this, and what we call as an emergent property. So this emerges as big, and comes to fore in a polymer. Okay, so we have now talked about the type of backbones, we have talked about the type of bases, and one question still remained in our mind at that time was, why a ribofuranos? So far we have argued about the bases, the PK minus beta, but why this ribofuranos? What is so special about the ribofuranos? So what we started looking at in our lab at that time, what's called a pentylose molecule. And this pentylose is a different isomer. So it's the same ribose, but now the so-called aldose, or the aldehyde form of it, is now changed from an aldehyde to a keto form. And there are other reasons why we considered the keto form, but the basic question was, if you are a ribose, why, or a sugar, why a pentose and not a pentylose? And that was the great. So again, as a synthetic organic chemist, we can go ahead and make these, and that's what we did. So two of my colleagues, they worked on it, and they made the ribulose, what we call a ribulofuranosyl nucleoside, and a xylylofuranosyl nucleic acid, and made variations. And here is the RNA, and you can see what is the difference. So the RNA has the phosphodiester backbones on the outside, the other side of this ribose ring, and the bases are on the exact opposite side. Whereas here, the bases and these backbones are on the same side of the sugar. And what we found after many instances was, unfortunately, despite the hard work of these people, these systems did not base pair. And any insertions of that led to a weakening of the base pairing systems in the RNA. So what we concluded was that, if these systems were around, they would not have competed with RNA. But what is more important is that just being there and being abundant is not enough that you will survive selection by chemical evolution. And leads to an important point. Being there and being useful are two different things. You are selected for your usefulness by evolution, not just because you are there. If nature does not find a use for you, you will not become part of the evolution, and you will be left behind. And that is biology. That is life. And there is no two ways about it. So biology is very, very strict in its selection, and it will take only the things, and that's the use of mutation. You mutate, and only the useful ones are selected. It's just like your antibodies. When you get infection, antibodies are there, and then the whole thing works only when the right antibody is there. So quickly, I'll just go to another system that we used, was an acyclic system. And what we found was, depending on the nature of the linker, again, this was a better base pairing system than this. But when we started putting things together with the pentylose system, so here is RNA. And what we did was, we removed this, the cyclic part of it, and made an acyclic system. So you went from a good base pairing system, and you lost the base pairing system. But in our case, where the pentylose, where there is the same cycle, but the bases are on the same side, we removed the cycle, and we made a better base pairing system. So here, we lost the base pairing properties, but here, by doing the same operation of removal of ring structure, we gain base pairing properties. And what's happening is, if you look very closely, this Watson-Crick phase of the base is facing the right way away from the phosphodiester so that they can base pair. But here it's facing the wrong way. And by removing the structure, we have made it face the right way so that we can base pair. But here, it has too much of rotation that it suffers from it. And so what happens is, the ribofuranose actually is holding the nucleobase in the right position, facing away from the phosphodiester backbone, so that you can make a duplex. So if you put all these things together, there is quite a lot of level. Each and every level, there is a selection, there is a demand that that happens. And you can see that this RNA, as a functional molecule, is expressed only in its very final form, not before. So that means you can't just look at ribose alone and decide I'm going to make an RNA. That's impossible. It has to come only when the whole molecule is made and that functionality is expressed within the ecology of the whole cell structure. So that is why we argue RNA is likely a product of chemical evolution. So in the final slide, what I just want to inform you is that, when we look at these type of chemistries, and we are, obviously, biased by what life is today, but you change the conditions or pH or change the temperature or the solvent, you will go to a completely different solution. And that is of interest to us. Are we alone? Are we the only life that is known in the universe? So what I want to end up with is saying that the molecules in biology that we have is a destination, and they are not a destiny, because if you change the conditions, you will come up with a different solution. Okay, just want to thank all my teachers. They laid all the foundation, and with that, I end my talk.